Let's assume that we have a SCIR model. Our goal is to figure out how many people to vaccinate. To do that, we want to understand the conditions in which a disease will spread. In other words, we want our E and our I compartments to increase. The dynamics for these equations can be expressed as dEdt and dIdt being greater than 0. Now, you don't need to know calculus to understand what's going on. All you need to understand is that the inflow of the pre-infectious compartment and the infectious compartments are increasing. So think of it like a bathtub. We have water coming in and water coming out, water flowing out, right? But the bathtub is not going to overflow if more water is flowing out than is flowing in. So these equations, being greater than 0, are making sure that the inflow is greater than the outflow for the disease to continue spreading. Now, as a reminder, beta represents contact. So if we get more people getting infected, if there's a lot of contact between susceptible and infectious people. And F is the rate at which people go from being exposed to being infectious. So think of it as as being related to the latency period. And R is the rate at which people recover. So this is the recovery rate. And this is the 1 over the latency period. You don't need to know about the details, but we do want to do some math with this. So we're going to combine the equations together, and we see that beta Si minus Ri is going to be greater than 0 because we have FEs on both sides. And placing Ri to the right side, we notice that we can cancel the i's. So all we do now is we divide both sides by r, and we get beta s over r greater than 1. Now, this depends on the time, right? So I'm going to denote this as RT. Why did I write RT? First of all, don't get confused with this RT, the recovered RT. This RT has to do with the disease being spread. You might have heard of the term R0. Well, that's just plugging in 0 into this equation. This is going to be beta S0 over R. But what does 0 mean? It means at the start of the infection. And notice at the start of the infection, basically everyone is susceptible. So if the population is defined by a number n, then we can write this as beta n over R. So R0 is basically where at a totally susceptible population, if a single infectious person goes in, on average, how many people will that person infect? And of course, this is an average value, so it's going to change. And it also depends on the disease. Notice that R, small r, has to do with the disease, but it also depends on the population size and also the social structure, the contact rate. People are trying to lower beta because it's the easiest one to lower. This is why governments are imposing social distancing levels everywhere. Anyways, this RT is what we want to focus on, this big RT. Okay? And R0 is also a fixed value because it's the value of RT at the beginning. For COVID, it's around 2 to 4. There are estimates for R0, but a lot of people disagree. Maybe I'll do a video on estimating R0. given the data. But this is hard to predict because social distancing levels are changing every time. For comparison, measles is around 13. So we see that measles is a lot more infectious than COVID. Okay, so how many people need to get vaccinated? Well, a better question would be phrased as what proportion of the population needs to get vaccinated? Okay, and because we are dealing with proportion, let's define another variable. So this would be the proportion of the susceptible population, right? But because we're too lazy, we're going to write this as small s, the proportion of susceptible people. Now, RT, big RT, which does not mean how many people have recovered at time t, but it refers to the R that epidemiologists like to refer to so much. This is beta S over R, but if we multiply, okay, and R0 is beta N over R. So if we multiply R0 by S over N, then we see that the N is going to cancel, and this is going to be RT. So recall that we need this value to be greater than 1 for the disease to spread, which means that if we want to stop a disease from spreading, we want this value to be less than 1. Okay, so this is going to be small s of t times R0. We want this value to be less than 1. In other words, we want the proportion of susceptible people to be less than 1 over R0. But we want to change this number or manipulate this equation so that we know how many people to vaccinate. So think of it this way. We have, at the beginning of an epidemic, we have basically everyone being susceptible. No one, maybe like one person is infected, but the model looks like that. So we have one person here, basically everyone here, nobody here, but what if we have a vaccine, right? So we can put people directly into the recovered group. Then the proportion of susceptible people will be small s of t, and the proportion of people who are vaccinated would be 1 minus that, right? So we want to know what this value needs to be. So I'm going to subtract st from both sides, and I'm going to subtract 1 over R0 from both sides, and I'm going to add 1 to both sides. And there we go. This is the population vaccinated, the proportion. Let's talk about the proportion. Proportion of people vaccinated needs to be greater than 1 minus 1 over R0. So for COVID, R0 was around 2 to 4. It's estimated to be around 2 to 4. Then we'll have 1 minus 1 over 2. That's around 1/2, right? We need around half of the population being vaccinated. But if we're careful, then maybe if we estimate R0 to be stronger, to be around 4, then we need around 3/4 of the population to be vaccinated in order to control the disease, in order to stop the disease from spreading. Of course, we want to err on the safer side, so we might want to go a bit over 75%. And we also need to note that this disease has been around for a while, so a lot of people have already recovered and are already infectious, so maybe this value doesn't need to be as high, but that's not for me to decide. I'm just showing you the math.